Hi all, myself Kalpana, assistant professor in electrical engineering department, Mlritm. My subject name is electromagnetic fields. Module 1, I am explaining about the electrostatics. In that, I am explaining the topic electric flux and electric flux density. So in the last class, I have discussed about the Coulomb's law and electric field intensity. So today I am going to explain about the electric flux and flux density. So first of all, what is electric flux? So electric flux is nothing but here we are assuming two charges are there, that is positive and negative charges, plus Q and minus Q. So if charges are present, there is a force of attraction or repulsion will be there. If the both charges are positive, then there is a repulsive force, and if the two charges are different charges, then there is a force of repulsion will be there. So these force lines exist from plus charge to plus Q to minus Q. So these are the force lines. These force lines are nothing but electric flux lines. These are nothing but electric flux lines. So it is denoted by symbol psi. So here it is similar to the charge. The unit of flux, electric flux, is coulombs. So the unit of this flux is nothing but a coulombs. So next we will see the properties of the electric flux lines. So here the flux lines are starts from positive charge to the negative charge. Means it will start from positive charge and terminate at negative charge. So that is the property, first property. So next, if the negative charge is absent, means only positive charge is present, then these flux lines will be terminated at the infinity. So means these, if only positive charge is present, these flux lines will be like this. So these will be terminating, means ending at negative charge. Okay, next, negative charge is at the infinity. Why? Because only one charge is present here. While the absence of positive charge, this electric flux terminates on the negative charge from the infinity. So that is the second property of the electric flux lines. Next, coming to the third property, there are more number of lines, means flux lines are more. Here we have positive charge and negative charge. So here more number of lines are there, means electric field is stronger electric field. And also these lines are parallel to each other. These never cross each other. These lines will never cross each other. Next, these lines are independent of the medium in which the charges are placed. Means if it is any medium, air or anything, these are independent of the medium, and also these charges will enter or leave the charge surface normally, means it will start and end here. So that is the sixth property. Next, if the charge on a body is Q coulombs, then total number of lines originating or terminating, originating means starting and ending it also at Q. So the total number of lines are nothing but flux lines. So this electric flux is nothing but psi equal to Q coulombs. If the total flux is nothing but here total charge. So according to SI units, this Q is large and flux is more surrounding the charged wire. Okay, so this charge is nothing but displacement flux. This electric flux is also known as displacement flux, and this flux is a scalar quantity. Next, we will define about the flux density, electric flux density. For that, I am considering two charges here, positive charge and negative charge. So the flux lines will be start from positive charge and end at negative charge. Here it is like these are the crowding of lines. So flux is starting from positive charge and terminating at the negative charge. Okay, so here the density means it's some area we are considering here. So that density, that is nothing but a flux density. That is nothing but flux density, electric flux density defined by D. So that is equal to flux per area. Flux per area. Total flux per total surface area is nothing but a flux density. See here. So psi is the total flux and S is the total surface area of the sphere. Here I am considering it is a sphere. So for that, electric flux density is defined as flux per charge, unit area or total surface area is nothing but a flux density, electric flux density. And here the units of this flux density is coulomb per meter square. Okay. This is also called as displacement flux density or displacement density. So that is nothing but a electric flux density. Next, so here I am considering this flux density due to point charge. So for that I am considering one point charge here at the origin and it is a sphere. Okay, here I am considering a point here. So it is in the direction AR direction. So these flux lines are originating from positive charge and radially outward direction. So flux is coming outside like this. So the area of this is R. Okay. So here we need to calculate the flux density at any point of the surface. Okay. So that is denoted by D. So this D equal to total flux by total surface area. So here I am considering this flux as charge. Okay. So that is nothing but total flux and surface area, that is nothing but total surface area of the sphere. So that S equal to 4 pi r square. As we know that sphere surface area is 4 pi r square. So from the definition of flux density, total flux by total surface area. Total flux is nothing but Q and surface area is 4 pi r square. From that we can define that D equal to Q by 4 pi r square. So this is in the direction AN equal to AR. If we consider at any point it is unit vector. AN is nothing but a unit vector. So it is in the direction of AR direction. So this is unit vector direction. So here I am considering only magnitude. If we consider it is as a vector quantity, then D is defined by Q by 4 pi r square into AR coulomb per meter square. So this is electric flux density due to point charge. So next, coming to the relationship between electric flux density and electric field intensity. So as we know that already we have derived that electric field intensity at any point at a distance r from the point charge is given by Q by 4 pi epsilon naught into r square into AR. This is also in AR direction. AR is a unit vector, R is a radius and Q is total charge. So before that I have derived the electric flux density, and in previous class we have derived electric field intensity as Q by 4 pi epsilon naught into r square into AR, and D is now we have derived Q by 4 pi r square into AR. By dividing these two, we will get the relationship between the flux density and electric field intensity. That is given by D equal to epsilon times E. E is nothing but a electric field intensity and D is electric flux density. So here epsilon naught it is for free space. So epsilon is nothing but permittivity of the medium. Okay. So this epsilon is the function of epsilon naught into epsilon r. Here epsilon naught is for free space and epsilon r is for relative permittivity. So for air it is epsilon r is 1. So D equal to epsilon naught into epsilon r into E. So the D is nothing but epsilon naught into E. So this gives the relation between flux density and electric field intensity. Next, coming to, so we are here flux density for various charge distributions. So charge distributions are nothing but we have line charge, surface charge, and volume charge. For every line, surface and volume, we are defining the electric flux density. So for line charge means I am considering, so it is a three-dimensional, that is x-axis, y-axis and z-axis. Here I am considering that line, in the line, this line we have a charge. So for in that case, here we have considering that uniform charge density rho L. So from that we are defining the charge Q as line integral of rho L into dl. Okay, so rho L is nothing but charge density, line charge density, but as we know that flux density is nothing but Q by 4 pi r square into AR. So in place of Q, I am substituting rho L into dl. If the line charge is infinite, so the electric field intensity derived as rho L by 4 pi epsilon naught into R into AR. So and also D equal to epsilon naught into E. From that we can replace that electric flux density as rho L by 2 pi R into AR. This is for infinite line charge. So this is electric flux density for line charge density. So next, surface charge. So for surface charge, I am considering one sheet of charge like this. So I am considering the sheet of charge, and here I need to calculate the what is electric flux density due to sheet of charge. Okay, so in this surface area, for that I am taking a uniform charge density as rho s coulomb per meter square. Okay, so then total charge on this surface is given by Q equal to surface integral of rho s into ds. Okay, so here we know the Q, so we can define D as Q by 4 pi r square into AR. So substituting Q value, that is rho s ds, we will get rho s D equal to integral of rho s ds by 4 pi r square into AR. If the sheet of charge is infinite sheet of charge, then as I already derived that electric field intensity for infinite sheet of charge as E equal to rho s by 2 epsilon naught into AR direction. So by replacing this in electric flux density, by taking the relationship between D and E, that is D equal to epsilon naught into E, from that we derived that D equal to rho s by 2 into AN. So this is for infinite sheet of charge. So first one is line charge, next one is surface charge, next volume charge. For that I am considering some cylinder of volume V. For that it has uniform charge density, volume charge density as rho V. So from the total charge enclosed by this volume is given by Q equal to volume integral of rho V into dV. So as we know that electric field intensity is given by Q by 4 pi epsilon naught into R square into AR. By substituting this Q value, we will get E equal to volume integral of rho V dV by 4 pi epsilon naught into R square into AR. So from that I am deriving equation for electric flux density, that is D equal to volume integral of rho V dV by 4 pi r square into AR. So these are various charge distributions. First one is line charge, surface charge and volume charge. Okay, so next coming to the Gauss law. So this Gauss law is fundamental law of electromagnetism. Here Gauss law states that total electric flux enclosed in a closed surface is equal to the total charge enclosed by that surface. It is nothing but if we consider some closed surface like this. Here I am taking some flux here, that is psi. Okay, so in total surface means this charge flux is nothing but charge lines. So these are total surface we are considering. This total electric flux is nothing but total charge enclosed. Okay, so that is a statement of Gauss law. So for that I am considering some point charge Q located at some medium with a dielectric constant. So the flux density at a distance r on surface enclosing the charge is given by D equal to epsilon into E. As we know that this D equal to Q by 4 pi r square into AR. So this is the statement of Gauss law, that is total electric flux through the closed surface is equal to the total charge enclosed by that surface. So for that also I am taking the elementary surface area, some ds, amount of flux passing through the element, this surface area is given by d psi equal to d dot ds. So as we know that d equal to q by 4 pi r square. Okay, so d psi equal to q by 4 pi r square into ds into cos theta here. So psi equal to means I am taking the integration of d psi. Why? Because we need to calculate the total flux. So total flux means we need to integrate the differential flux. So in the area ds. So psi equal to integral of d psi, that is surface integral of d dot ds. So this is the Gauss law. Okay. So irrespective of the shape of the surface and charge distribution, the total flux passing through the surface is nothing but a total charge enclosed by that surface. That is psi equal to closed surface integral of d dot ds, that is equal to q. So this is Gauss law. So for this also we have many terms here, that is line charge density, surface charge density and volume charge density. So for that we need to define the Gauss law. So if there are number of point charges are present enclosed in a closed surface, that is q1 to qn, then total charge is nothing but q equal to q1 plus q2 plus up to qn. So for that, from that we define the total flux as psi equal to q, that is sigma of total charges. Okay, if there is a line charge with charge density rho L, then we can define this flux as psi equal to q q. Why? Because from the Gauss law, so line integral of rho L into dl. If the surface charge density is present, then psi equal to rho s into integral of rho s into ds. If the volume charge is present, then psi equal to closed volume integral of rho v into dv. So by commonly mathematically we can define Gauss law as psi equal to q equal to closed integral of d dot ds, that is equal to volume integral of rho v dv. So these are the charge distributions for all charge distribution, that is line charge, surface charge and volume charge. Okay, so I have taken this from the William H. Hayes. References are William H. Hayes, Engineering Electromagnetics, Tata McGraw-Hill edition, and also MNO Sadiku, Elements of Electromagnetics, and also Pramanic Electromagnetics, Problems with Solutions, Prentice Hall, India, and also I have taken from A.U. Bakshi and V.U. Bakshi. Thank you.